Imagine a world so remote that sunlight takes over 5 hours to reach its surface. Out here, temperatures plunge to minus 230 degrees Celsius, cold enough to turn a glass of water into rock-solid ice in a single second. This temporal scale is difficult to grasp. While Earth completes a lap every 365 days, a single year on Pluto takes 248 Earth years to complete. If you were born there, you would still be decades away from your first birthday. For 76 years, this frozen outpost held the title of our solar system's ninth planet. Then, in 2006, the scientific community voted to strip that title away. Pluto's story is a case study in the evolution of science. It shows how the development of more powerful telescopes and sensors eventually forces us to rewrite our maps of the universe. In 1930, the search for a hypothesized ninth planet led researchers to the Lowell Observatory in Arizona. Leading this search was Clyde Tombaugh, a 23-year-old astronomer tasked with mapping the furthest reaches of our solar system. Tombaugh used a mechanical process to compare photographs of the same patch of sky taken on different nights. He looked for any tiny speck of light that appeared to be moving against the fixed background of the stars. Once he spotted the new world, the naming suggestion came from an 11-year-old girl in England. She chose Pluto, the Roman god of the dark underworld, to match a sphere sitting billions of miles into the frozen darkness. This discovery became a pillar of 20th century astronomy. However, as our understanding of physics deepened, the charm of Tombaugh's find collided with the need for a more precise scientific definition. In 2006, the International Astronomical Union gathered in Prague for a vote, changing the textbooks. To resolve the status of several newly discovered objects, scientists established 3 specific criteria that any body must meet to be officially called a planet. It must orbit the Sun and be spherical. Pluto passes. But it fails the third rule, clearing its orbital neighborhood. Because it sits in the Kuiper belt, its highly tilted, elongated path, which crosses inside Neptune, remains cluttered with icy debris. This failure to clear its path led to Pluto's reclassification as a dwarf planet. It was a decision based on the mechanics of the solar system rather than the tradition of our previous maths. Ironically, NASA launched the New Horizons mission in 2006, just exactly as the debate over Pluto's status reached its peak. Traveling at 58,000 kilometers per hour, the spacecraft still required a 9.5-year journey to cross the void between Earth and the Kuiper belt. In 2015, the probe revealed a world dominated by a massive heart-shaped plain of nitrogen ice. High-resolution data proved Pluto is geologically active. We also observed Pluto's largest moon, Charon. It is so large relative to Pluto that the two bodies orbit a common center of gravity located in the space between them, creating a double planet system. The surface features water-ice mountains rising 3 kilometers high, rendered hard as rock by extreme cold. These peaks are surrounded by slow-flowing nitrogen glaciers. Pluto even exhibits an atmospheric cycle where it appears to breathe. As it nears the Sun, surface ice turns into gas to form a thin atmosphere, which then collapses and falls back as snow as the world moves away. Ultraviolet radiation reacting with surface methane creates tholins, which give the landscape its distinct reddish-brown tint. The New Horizons mission provided a profile of a world with geological and atmospheric complexity comparable to the larger official planets. The most significant finding from the mission data was the possibility of a liquid subsurface ocean hidden beneath that frozen crust. This process is driven by the radioactive decay of elements within Pluto's rocky core. That internal heat can radiate outward, melting the bottom of the ice shell and maintaining a layer of liquid water despite the surface temperatures. This creates a potential environment similar to Earth's deep-sea vents. In our own oceans, these dark, high-pressure zones support microbial life that survives on chemical energy rather than sunlight. Evidence of liquid water at the edge of the solar system suggests that the conditions necessary for life can exist in far more diverse environments than we previously imagined. The 2006 demotion was not a loss of status, but a step toward a more accurate inventory of a solar system that is far more crowded and diverse than we realized in 1930. Science is a self-correcting process. As our sensors provide better data, we are obligated to update our classifications to match the physical reality. Whether we classify it as a planet or a dwarf, Pluto remains a geologically active world with its own moons, a dynamic atmosphere, and potential hidden oceans. Its story reminds us that the features of the universe exist independently of the labels we use to describe them.